Other prompters so we can get to the bar with Gianni, who will be telling us about scalability and accuracy.
So another quick announcement. There's a group photo right after all of this. That's the only thing we can say. So please stick around to do the group photo.
Okay, thank you. I'm going to talk about relative binding affinity and towards scalability and accuracy. We have not done a lot of relative binding affinity before. In fact, I never ran FEP in my life. But we've done certain things along the way, and we were particularly interested in this about this a little bit because of the OpenMM thing, and a little bit because in Stellar we started to make molecules, and we wanted to make only good molecules. So we started, I think, this in June last year, and it's a little bit of a practical talk. In fact, I keep it limited to 15 minutes, so we have the time for questions. And 20 minutes, 25 minutes, yeah, 20 minutes. Okay, so we done some work on binding affinities. We used everything but FEP practically, and so in particular we started with PMFs, so that where you do it by stratification, umbrella sampling, like what Benoit Root was doing back then in 2010, like to compute absolute binding affinity for peptides and things like this. It worked reasonably well, but it's super expensive. Like for one, you needed 100 microseconds to equilibrate one of these things. We looked even if you could do something faster with StereoMD, both one way and with Crookes formula. Again, this wasn't super strong, the convergence, but I mean, we could get something. We worked a lot in Markov-Stein model that will give you a full reconstruction of everything, including the binding affinity. But again, this is like several microseconds, tens of microseconds to do one ligand. We looked at faster ways, like linear interaction energies, but we, in our end, at least, is a lot of work to having kind of the same cost of glide or any of these things. And then we even looked at deep learning methods like KDeep in 2018, and delta delta for relative. So this is the only relative thing, but they're all machine learning fast things. This actually won some sub-challenge in the D3R challenge for prediction of binding affinity. But this was normal deep learning methods, so no physics. And we were looking for having in OpenMM some kind of good binding affinity methods, which was scalable to the future. And that's I'll say what we mean by that. John proposed to look into ATM by Emilio. And the reason why we liked it because the reason I liked it because it seems like a natural extension to the PMF, just alchemical, but it offers this kind of simple strategy. It was good for scaling because it's easy to set up, so you don't have to get mad if you want to run thousands of things. And it was good for accuracy because it works for anything, so we could use it for neural network potential without having to do sophisticated things. So once we had that done, this is what. The only thing that wasn't super sure is what was tested in some system, but not many. So we wanted to make sure that it was kind of working well. And of course, it uses this standard force field for the Amber force field. And we would like to move beyond that, like John said. And one of the reasons is that this is a very many body terms. I mean, it has two body, and then 3 body, and 4 body, but all for torsion and short terms. And there is a natural way to have more many body terms and in terms of machine learning potentials. Machine learning potential is something relatively simple. So you use some sort of function approximator through a neural network, usually, that takes all your coordinates and spits out an energy. And because this thing over here takes very high dimensional data, naturally, like think of images, videos, and so on, but in this case, it's just coordinates. And it's differentiable, so you can just do differentiate this and get forces. So this is just a natural way to do it. And automatically takes into account all the many body terms that you want. You need to have some restrictions, so you want to have some physical constraints, so it needs to be translational, rotational, and permutational invariant, need to have energy conservation, equivariance, and so on. And there have been, now I'm going, for sake of time, I'm not going inside this plot, but just each of these is a method. And this slide maybe is 3 years old, and there are as many now. And each line is a method, and so you see the more data you give for training, the better it goes in the error. And the better is the method, the lower is this thing. And I think at this point we are something like here. Okay, so we are really progressing very fast. And we're working a little bit on that. And so we published this in iClear 2022, where it was kind of the state of the art. It's a method that we're looking for doing. So all this field was mainly initiated by material people because it's much harder for them to do force field like we do. So we're looking for methods which are not, doesn't matter that they're super accurate. We already get very good accuracy in learning quantum mechanical data, but we would like something that is faster. And so anyway, we did this transformer-based method, which was equivariant. We're coming in a couple of weeks. We're publishing another one, which is even more sophisticated than this, and is very interesting. Another job that we did inside the OpenMM was to kind of, together with Peter and John and people, Ramonda from Accelera, to kind of make available all our infrastructure for people to use machine learning potential. So on one side, we did TorchMD, which is not here, but it's kind of a PyTorch MD code, which is end-to-end differentiable. And it's easy in that to play around with machine learning potential, but for speed, you want to use something like this. Now with OpenMM 8, it's relatively easy. Another thing that we wanted to do is to be practical. And you have in a number force field set, maybe you have some hundreds of parameters. In a machine learning potential, you have maybe hundreds of thousands or millions of parameters. So you cannot, it's impossible to make up the speed. You cannot have a machine learning potential which is as fast as normal molecular mechanics. But one thing that we can do is to kind of borrow from QMMM and do a neural network potential MM kind of thing. But the very simple one where we say, okay, there are some parts of the systems which are treated molecular mechanics, some others which are treated with neural network potential. For instance, this is the small molecules, and this is water and proteins and everything else. And there is a coupling term, which could be very simple, like intramolecular, we just use neural network potential, and inframolecular, we use molecular mechanics. And by doing this, we get kind of the best of the two at reasonable speed. Reasonable speed means that these are the latest benchmark on a 4090, means that before we started this optimization with an NP-ops and so on, it was kind of 100 or 200 times lower compared to molecular mechanics, and now we are 10 times lower with a time step 2 difference, so it's kind of 5 times lower. And if you consider the amount of difference in calculation that is doing, that is impressive. I think there is a lot to do. This machine learning framework are not designed for latency, which is what you do in molecular mechanics, in dynamics. No? So you want very fast kernel execution, but without latency. Well, all the machine learning with all the machine learning methods and PyTorch and so on are done for batching, so the kernel initiation and so on is just too slow. And NVIDIA is helping a little bit with this, but there are a lot of things to do still. Anyway, I think 5 times, at least 5 to 10 times, is usable to do some tests. And then in this second part, I'm just talking this first validation. So we said, okay, let's take ATM. We have all the infrastructure, and let's look how it works. And we just published this paper, I think, a few weeks ago, trying to test on very naively on some on the Schrödinger set for FEP. And what we found was the methods was actually behaving well. So we had correlation. This is GAF2, so nothing fancy in terms of force field or anything, just very quick and dirty. We did, and we had the reasonable correlations and between in all the pairs. Maybe you see better here. So we compared ATM against FEP plus. These are the paper. We didn't rerun their calculation. I don't know if they have anything better now. So it's FEP plus, Amber, TI, and PMX. And first of all, they kind of, and this, they also change force field, no, between one and the other. But overall, first surprise is that there's not much of a difference. The ATM, especially in correlation, is pretty okay. Maybe sometimes it's the best, sometimes it's the worst, maybe here, but not special. In MAE is usually a little bit worse, okay? So it's a little bit, that's usually a little bit higher MAE, but the recovery is in the correlation. And usually it's because it's like it can't, maybe this is because of the methods or because of the force field, we don't know yet. So we said, okay, this is reasonable. We rewrote now, so these are the steps that you go through when you do ATM. This part is done by OpenMM, which is the main, what Emilio showed before. We rewrote the first equilibration this first part. We automated this first part, and we rewrote replica exchange because it wasn't running well when we were running in GPU Grid. GPU Grid is a kind of a distributed, similar to Folding Atom. It's a distributed project where we have some 1,000 GPUs there. And we're calling optimizing for performance, both OpenMM and people in Accelera. But we already get around 300 nanoseconds a day, which a system of this size, you should get around 900, 1,000. So at the time, it's 3 times lower than running the normal MD because of the way that it works. So you can actually currently do 5 to 6 pairs per day per GPUs. And in GPU Grid, we're actually doing around 1,000 per day. We wanted to test all these different force fields and see how they worked. So we have a parameterization tools, which just does the normal thing, torsion assignment, charge assignment, and so in torsion scanning. So and you can use all sorts of potential, XDB, Psi4, or ANI, or TorchMD-NET, or whatever. And it creates a number force field output file. And the idea was, okay, let's test a little bit more systematically what's the impact of the force field. And so we've done this combination so far. So for the protein, we use always FF14SB, and then we use GAF2, OpenFF2, OpenFF 1.2. We started this, but we get some weird results, so I'm not going to show you this. And we're doing this, and then we will be doing the neural network potential. So all this part is a little bit preliminary, but I think maybe you can tell me something, because it was a little bit surprising for me. So these are the results. So for everything we've done either 5 replicas. For every pair, we did 5 replicas or 10 replicas, 5 to 10 replicas for each pair. And again, we see GAF is not doing too badly. The black means best across the line. We tested GAF2 here, OpenFF 1.2 and OpenFF 2.0. OpenFF 2.0 does seems to be better than OpenFF 1.2, but I don't see a significant improvement. No? Sometimes GAF2 is better, so we're still a kind of a level that is not, I mean, at least in our end, is not particularly better than GAF2, and this was a little bit surprising to us. These are the results. You see that it tends to be stretched more, so the prediction are usually like this. This maybe is the method, it's not the force field, but Okay, here is quite okay, but for instance, here is kind of more elongated than what you would like it to be. So that's why the MAE comes a little bit higher than the other methods, but the correlation is okay because it still respects the ranking, but it does is a little bit less accurate. Okay, so this is the same for OpenFF2, and so this is comparison for ATM with Sage and ATM with GAF2. And again, we also put FEP plus and PMX for reference. And this now has more replicas and so on. So we get actually in average worse correlation for OpenFF2 and marginally better here for FEP plus or GROMAX here. For ME is the same kind of results. So we also done, as I said, we had replicas. I said, okay, so if we want to run these things, what should we run? Should we run one replica per pair? Should there 3 replica per pair? 10 replica? Doesn't even make sense to run replica. And so we've done this type of plots to see what was the case. So here we have the MAE, and here you have the standard deviation of the results. So in this case, we ran 4, and in this case, we ran 3, and in this case, here we ran 4 again, and so on. So what this means is nicely we don't have any point here. So we don't have any point where we run multiple replicas, and the absolute error, the mean error, is high, but the standard deviation between the replica is low. So we can use the standard deviation between the replicas to say, to eliminate some of these points. So, so it has this nice shape that if you have low standard deviation, 0.5, let's say, you kind of know that it's decent. This is a common thing that we do in machine learning. So we have multiple models, and then we see the standard deviation across the model almost finished. And so this would suggest that if you want to be safer, I saw yesterday Anna that was doing 3, and yeah, I think probably 3 is enough. You do 3, and then you check if you have low standard deviation between the 3, then your model kind of knows what's going on, and you can trust a little bit more the results. Okay, so I just conclude here. So we're trying to validate ATM. The idea is to run it at scale and extend it to non-network potential to see how accurate can we get. The main interest is to have a method to be usable for neural network potential. That's why we started this activity. So we're finishing now test on the standard potential, which was just for practice practically. And I don't know, we would like to try this new potential, maybe see the difference between OPC and TIP3P. We definitely would like to try a neural network potential with TorchMD-NET and ANI and see how it goes. There will be some new potential coming out for TorchMD-NET, which allows for all the elements and charge and non-charge molecule and so on. We'll probably extend targets for validation, and I'm really keen to have suggestions from you because you probably know more than me in what we should do or should not do. We have a capacity to do thousands of pairs per day, and the interest is to see if we can do something that is scalable but super accurate. Thank you.
Questions for Johnny? I only have one suggestion. If you want to use the GAV2, I highly recommend that you use the retro charge because it's developed to use the retro charge. And if you want to pick on the fast charge such as ACEMD, I think GAV is better.
Okay. So try different charging model.
Yeah.
In your calculated versus experimental free energy graphs, you pointed out this as puzzling, this almost systematic slope less than 1, whereas I got often a systematic slope greater than 1 with the non-equilibrium switching. My pathology puzzles me. Do you have any understanding of this systematic or tendency towards slope less than 1?
What do you plot in the x-axis? Are we plotting the same thing? Mine is predicted in the x-axis and experimental in the y. But I saw others that do the opposite. So maybe we just invert in the axis. Yeah, sure. If it's common to do the opposite, it's because we're ignorant, as I said at the beginning. So we don't know what's common. Yeah. So we should plot the opposite then, experimental on the x-axis. Oh, okay. I think it's, I mean, maybe it's the method. Yes, maybe Emilio can say more, I don't know.
Yeah, I think maybe it's the method, but it still puzzles me, like, what is it?
So it strikes me that you're able to run calculations, very efficiently with a high level of precision. I'll bring it up to the general audience. One of the things that's very challenging in our field is being able to get highly precise calculations. And one of the ways that one can do it, the hard part, which you sort of showed in your talk, is you're doing a lot of calculations where you're doing with some potential a bunch of alchemical free energy calculations and getting some pretty precise results. It would be interesting as a community if we thought about how we might be able to really collect highly precise reference calculations so that you could test new models just by endpoint corrections. If the middle leg was sufficiently precise, like you're sort of presenting here, I just wondered if you had some thoughts about building infrastructure where we could use a certain reference potential in order to create benchmark databases for tricky alchemical, because it's the alchemical steps that are usually the harder parts. Correcting the end states from one model to another is usually a little bit less demanding. That might be a good community-wide resource for us to all discuss at some point.
I'm not sure we are precise nor accurate. I mean, I show you that we are both not precise and sometimes not accurate. The only thing you get is that when you're precise, you're usually accurate, which is already something. But I don't know. As I said, I'm not.
Yeah, just a quick one. Did you already result as the relative variance where you swap every compound, or did you also try the variance of the absolute?
No, we barely tried the absolute, but no, we're doing only relative at the moment. We want to, that's another advantage that we were to try to do absolute, but we haven't tried seriously now. We tried just quickly and it didn't work, but we just tried very quickly. He's not super supporting on that anyway, he's always saying that doesn't work. But now we will try for the absolute as well, but at the moment we just done, we want to get to something, to relative, and then we'll see. I don't think it will take much longer because we can do so many calculations, but see, I don't expect this to go. I'm a little bit disappointed that I was expecting, okay, I get better and better force field, and then I reduce it, so when I go to the non-neutral potential, then I have a very accurate thing, but it seems that there are lots of, we discussed it with John, there are a lot of other things, water, proteins, pairing the potential that makes maybe a bigger contribution than the potential of the small molecule itself. So you need to kind of fix everything, not one thing.
All right. Let's thank Gianni again.
Thank you.